This video is sponsored by Opera. This is a totally custom handheld computer I designed and built. It can do all the things that a full desktop PC can, but in a tiny form factor. And in this video, I'll show you exactly how I made it. When I was a kid, before smartphones took over the world, I always dreamed of having a full computer in the palm of my hand. But in 2007, something happened that changed the course of history. Apple released the first iPhone. And from that day forward, most of the things that we used to do on the computer would now just be done on our phones.
He told me this. He said, "You had me at scrolling."
Basically, handheld PCs never really got off the ground because smartphones kind of stole their thunder. And don't try to tell me a phone is technically a computer. Yeah, I see you type in that comment. Alright, so handheld computers do exist, and they did make some minor waves in the 2000s. Sony Vaio UX, OQO Model 2, others. They were referred to as ultra-mobile portable computers, and some of their designs were wild. However, none of these really caught on. They were glacially slow, had similar ergonomics to a paving stone, and cost more than my first car. But despite all of that, I still want one. So let's just build it. I mean, how hard could it be? The most obvious place to start is the computer itself. Now, there's a few options here, but due to size constraints, the best thing to do is to just use a single board computer or SBC, such as the Raspberry Pi. But in a previous video, I made a tablet-style cyberdeck with a slide-out keyboard, and for that I used a LattePanda Mu, which looks like this. I like these because they're x86 and they outperform even the Pi 5 by a decent margin. Plus, I already went to the trouble of designing my own custom carrier board for it, which works great and is just the right size for this project. So I'm gonna go with that. No need to reinvent the wheel. If you want to learn how to design your own board, you're in luck, because I already made a dedicated video about it, so go check that out. This board gives me 4 full-size USB ports, a full-size HDMI port, M.2 SSD and Wi-Fi slots, and these 2 internal USB connectors which I can use for a keyboard and audio. It's also got a side-mounted power button and a couple different power connectors. I'd say that's a pretty respectable lineup for a machine this size. I added a 1TB SSD and a cheap Wi-Fi card with some antennas to get things up and running. Now, this LattePanda Mu did come pre-installed with Windows, but it's almost like you guys may have some strong feelings about that subject based on previous comments. It's not a cyberdeck if it's running Windows. And you use Windows? Worst thing ever using Windows. Bro went through all that effort just to put Windows on it? Windows? Really? It's pretty cool and all, but Windows 11? Dude builds a field hacker's dream and puts Windows on it. Oh, what the? Windows? Windows running on a cyberdeck? Instant disqualification. Sorry. So I caved to the pressure and put Linux on it. There. Are you happy now? Or do I need to download Temple OS to satisfy you? All jokes aside, I do like Linux Mint, and it's running beautifully on this device, so that's what I'll be using. With all the research and design work that goes into my projects, things can get complicated and confusing fast. But at least your web browsing doesn't have to, thanks to this video's sponsor, Opera. I especially like Opera AI. It's built directly into the browser. No extensions, no extra tabs, and no account required. It's easily accessible in the top right corner of the browser. Here, I used it to find and explain what the different pins of this microcontroller do. You can see this nicely summarized breakdown right here. Opera's tab islands let me separate my workflow by grouping related tabs together. Here, I put all the info I needed about the battery charger I'm designing in one group, 3D models I needed for my project in another, and so on. Each group can be renamed, and you can assign a color to each one to keep things organized. Your most recently visited tabs are subtly underlined thanks to tab traces. The darker the underscore, the more recent the visit. The split screen feature is a game changer. Rather than jumping back and forth between tabs, I can keep 2 pages open right next to each other, or even see 4 at once in a clean grid layout. With this, I can compare spec sheets of different parts at a glance without having to switch back and forth. Listening to music while working helps me stay focused. Opera's floating music player, which supports 7 different streaming services, lets you control your tunes without having to stop what you're doing. You can even drag it outside of the browser, perfect for when you want to adjust your soundtrack while designing a circuit. Opera is free and packed with tools that make browsing smarter, faster, and more enjoyable. Grab it now using the link in the description. Next up, the keyboard and mouse combo. Because I have touchscreen fatigue. To be fair, they do have their uses, but I'm still a big fan of physical controls. Now, the whole point of this thing is to be usable handheld, so that means thumb typing. In my previous builds, I've used mechanical keyboard switches, which are fantastic, and very easy to work with because they just pop onto the keys like this. However, even the smallest ones are simply too big, unless we want a keyboard with like 20 keys. So I'll need to find another type of switch. Now, I was tempted to just use one of those little handheld Bluetooth keyboards off of Amazon, but I find them rather ugly and cheap looking, so we're not going to do that. The next choice was to just use these little micro switches, but they're low quality and not really meant for heavy use. No thanks. So instead, I went to some part supplier websites and found something that I think will work. These little surface mounted types are much higher quality and rated for like 2 million presses. So basically, I just need to design a PCB to hold these. I'll still have to figure out how to make my own keys though. But I also need a mouse, and space is very limited. In my first Cyberdeck video, I used this mini trackball, and something like that could probably fit here. That worked okay, but I think I'm going to use something different here. What kind of controls would be small, lightweight, cheap, and accurate enough for most uses? How about the thumbstick from a Nintendo Switch Joy-Con controller? They seem to fit the bill and they're easy to buy online, so I picked up a couple. They connect using this tiny little flat cable that clamps into the controller. The trick was figuring out which pin did what. Once I knew that, I hooked one up to a Pi Pico microcontroller using this little breakout board. I created a QMK profile to make it act like a mouse. Luckily, this was pretty easy. I also wanted a scroll wheel that I could control with my other thumb, so I bought a couple of these horizontal ones, which are super cool, but they were not cheap. I added one of them to the Pico setup and now had maybe the world's smallest and ugliest mouse. All of this stuff needs to go on a custom PCB so that I can mount it in my handheld computer. Here's what I came up with. This design lets me reach all of the keys with my thumbs, as well as the scroll wheel and the joystick. I also added these two little sockets, which will allow me to add some trigger buttons that I can press with my index fingers while holding it. For those, I'll be using regular keyboard switches, since I have a little bit more space there. All this stuff obviously needs a microcontroller to talk to the computer though, and we don't have the space for an Arduino Pro Micro or Pi Pico like my other previous projects. So I had to take a little bit of a detour and learn how to integrate an RP2040 microcontroller into my keyboard design directly. This is located on the underside of the board and has a USB-C connector, which will go to the internal USB port on the Mu carrier board via a custom cable. Interestingly, this means that I can use it to control any computer I plug it into, kind of like a gamepad, which is pretty neat. Up here, you'll notice this 3-digit 7-segment display and another large microchip. We'll come back to that and the keys themselves later. For the screen, my initial plan was to use this 7-inch touchscreen sold by DF Robot, the parent company which makes the LattePanda Mu. It's compatible right out of the box and the right size and not terribly expensive. So I bought one and started testing it out. And I wasn't super impressed. It's not a bad screen by any means, but at only 1024 by 600 pixels, the image clarity leaves a little bit to be desired. To make matters worse, it's got a rather large bezel around the edge, which to me is just wasted space that makes the whole thing bigger than it needs to be. And to top it all off, it's limited to 60 Hz. So naturally I went looking for an upgrade, and found this. Still 7 inches, but with a resolution of 1920 by 1080 and a refresh rate of 120 Hz, and a much thinner bezel. That's what I'm talking about. The important part though is that this is an EDP display, basically a variation of the DisplayPort protocol, and that's important because it's what the Mu uses. It looks way smaller than the other one, but the actual diagonal measurement of the screen is the same. It came with this driver board, because most people would probably use it with an HDMI input. But my plan is to cut out the middleman and plug this straight into the Mu's EDP connector. To do this, I needed the right kind of cable. And as it turns out, there are multiple versions with different amounts of pins and different spacing. And of course, the one it came with wasn't the right one, because why would it be? That would be way too easy. Fortunately, I did find the right one on eBay, but sadly, it didn't work. The screen was just totally black. So what's the deal? I peeled back the black plastic that protects the screen circuit board to try and do some diagnostics. The display seemed to be getting power, but there was no video, and the backlight was off, which seems suspicious. After digging around a while on the internet, I managed to locate the screen's model number and the datasheet, and I think I found the problem. The pin configuration of the LattePanda Mu doesn't exactly match that of the display. Now, if you peel off the cable's wrapper, you'll find these 40 individual wires that go to each pin. So I figured maybe I can just cut the cable in half, then resolder the pins to the right ones on the other end. Honestly, I knew this was a bad idea to begin with, but I was still prepared to do cable surgery until I found this. Each of these individual cables is wrapped inside of a ground shield layer, so the interior wire is even smaller than I thought, and probably needs that ground layer uninterrupted. So trying to do this by hand would be an absolute nightmare. Time for plan B. I decided to make a tiny little PCB that basically moves the wires over to the correct pins. So the first cable goes to the board, reroutes the pins, then goes out to the screen. Luckily, this was a fairly straightforward job. I almost forgot after all the trouble with the screen, but this computer does need some speakers. I previously used a single 40mm unit in my last Mu-based design. That was a really nice one, but it was a little bit too bulky to fit here. So instead, I got these two little flat oval shaped speakers. Just like last time, I'm using a USB audio device to output sound. This is because the I2S audio that the Mu claims to support still isn't working, sadly. I had to crack this USB unit open and solder on some wires which connect to a port on the carrier board. I'll be mounting these at the bottom front area of the device where hopefully they'll be easier to hear. The biggest struggle of this project though was the battery. But wait, what's so hard about that? Didn't you just repurpose a 12-volt battery bank from Amazon in your last Cyberdeck build? Yes, I did. And that's easily the worst part of that project. In most respects, this computer is awesome, and I really enjoy using it, but the whole power system sucks, if I'm honest. For starters, there's really no way to tell how much juice is left in the tank, so you can just be using it and it'll randomly shut off. I did come up with this little thermometer-like device which reads off the voltage, but that was really an afterthought. And when it comes to battery capacity, voltage alone doesn't give you a very accurate idea of the remaining capacity at all. Basically, it doesn't scale linearly with real capacity. Plus, the actual battery life isn't that great. The unit I bought on Amazon claims to have a capacity of 6 amp hours. I find that to be pretty optimistic. But wait, it gets worse. This is a 3S pack, 3 cells in series, meaning the operational voltage is 9 to 12.6 volts. And it doesn't have an output regulator, but the Mu needs a minimum of 10 volts. Are you starting to see the issue here? I'm losing a decent chunk of capacity right off the bat. I can get around this by using a 4S pack instead, which won't ever go below 12 volts. It has an integrated battery management system, or BMS, which is kinda mandatory if you don't want to end up on the local news.
Hellish flames consume a family home.
I still need an actual charger though, and a way to monitor how much battery I have left. But here's the problem. I'm already almost out of space with all the parts that I've tried to fit in here so far. So I can't just buy some bulky module and jam it in here. Oh, and I want this to be charged using USB-C like any other modern device. So you know what that means. Gotta design my own. I mean, how hard could... Wait.
One eternity later.
Okay, so that may have been a slight miscalculation. I spent weeks trying to understand, then design, then finally produce my own high-power battery charging, monitoring, and capacity displaying PCB. And this stupid thing didn't even work properly. I foolishly cheaped out and only paid to have 2 of these boards assembled. The first one met its tragic end when I accidentally plugged the battery in backwards. Yeah, I know. The second one seemed to be working at first and then stopped, and I really have no idea why. But in any case, this was a pretty major setback. Now, before you question my sanity for going so deep down the rabbit hole on a side project like this, just realize that this was something I wanted to learn anyway. Think of it like a tech tree that unlocks the ability to power up, pun intended, all of my future projects with their own high-quality integrated battery systems. But I also wanted to actually finish this project, so I had to find a compromise. While doing research for my own design, I stumbled across this. It uses the same chip that I was designing around, the BQ25792, and USB-C. Nice. Better yet, it has breakout pins for I2C, which again, I was already planning to use. The downside is that it seems to be capped at 5 volts for charging, unlike my design which goes all the way up to 20. That being said, it can still charge my battery pack all the way up to 16.8 volts due to an integrated boost regulator. It just won't be fast charging like you get from a modern smartphone, but I can live with that. After whipping up some code to run on the ATtiny that's located at the top of my keyboard PCB, I connected it to the charger via I2C, testpad saved the day here, and got it displaying the capacity as a percentage of remaining voltage. Like I said before, this is not the most accurate way to determine this, but it's better than what I had before, which was nothing. So at this point, I really thought all of my problems were solved, at least well enough to finish up the project. So I connected everything together for a test: the main computer, keyboard, battery, and charger. When I flipped the power on, the computer did start booting up, but I immediately noticed a horrible smell, and the next thing I knew, smoke started coming out of the vents. Then it shut off. I freaked out because I thought that the battery was going to catch on fire, but It was actually fine. The charger PCB, on the other hand, not so much. All I could figure was that maybe I had simply tried to draw too much current through it, but I now believe that it was something else, which we'll get to in a minute. In any case, it was back to the drawing board again. And if I couldn't find a solution, the whole project was dead in the water. I decided to just bite the bullet and redesign my whole battery charger PCB. I'll spare you the details here, but this is something that I plan to make a dedicated video about in the future because I think it's very useful information. This was a ton of work, but the most annoying part was having to wait a few more weeks to see if it would even function. Let's rewind a bit though. While I was waiting for my circuit boards to come in the mail, I was working on finalizing the shape of the device's outer shell. Whenever I'm designing a system like this, there's a lot of back and forth between concept sketches, 3D modeling, and PCB design. Usually, it goes something like this. I start with a general idea. In this case, handheld computer. Then I draw a rough sketch of what I think it would look like, throwing in some basic design elements to get an overall idea of the aesthetics. Next, I start looking for what parts I could use to actually make the thing. So once I have most of the required components figured out, I start downloading models if they already exist and making my own if they don't. When I have everything in one file, I fit it all together and that helps me figure out the dimensions for the custom PCBs I'll need to create. Once I make those, they get exported from KiCad and added back into the main file, and I can model the outer case or enclosure with the appropriate openings and mounting points for the interior parts. As I'm working, I'm routinely 3D printing different iterations to get the fit just right. And that's exactly what I did here. The final version of the case is made up of two parts. A rear shell that I got printed from translucent resin, which holds all the main parts in place, and a faceplate machined from aluminum and anodized in what I thought was going to be a cool color. They called this color champagne, but it looks more like some kind of weird flesh tone to me. And I was pretty set on that golden bronze color from my initial renders. So I primed, painted, and clear coated it. Now that looks way better. Earlier I mentioned making my own keys. I couldn't find any pre-made ones in the correct size. So I modeled these in Fusion 360, but I still had to figure out how to actually make them. The original plan was to get them resin 3D printed by a company, but I wasn't really sure how I was going to make the letters stand out using a single material. Paint, maybe? Instead, I opted to just print them myself using my regular FDM 3D printer, which supports multi-material printing. But I wanted these to look a little bit higher quality, so I picked up a 0.2mm nozzle, which gives me much better detail on the characters. While the replacement charger PCBs were still in production, I was trying to fix a few minor issues with other parts. The joystick kept drifting, and I noticed that the two microcontrollers on the board were getting strangely hot. Then I found something kind of disturbing. A short circuit on the keyboard. That's not good. Apparently not bad enough to make it stop working, but enough to make the chips get really hot. Ow! This made me question what had really burned up the charger. To clarify, the ground on the keyboard and the charger are connected, so if power was getting fed in there, well, that would be really bad. So did I really draw too much current? Or just short it out? Unfortunately, I didn't discover this until after I had already done all that work redesigning the charger PCB. After what seemed like forever, my parts showed up in the mail, and to my pleasant surprise, they actually worked. Nothing caught on fire, no smoke came pouring out this time. I might actually be getting the hang of this. Now they do have some weird quirks and design oversights, but you know what? Good enough. Let's just get this done. With all the parts in hand, it was finally time for assembly. The big trick here was fitting everything in such a tight space, and I wanted it to look somewhat neat because of the translucent shell. Most of the internal parts are secured by little M3 bolts that go into threaded inserts. All of this stuff has to go in here before I can put the front panel on. The switch over here isn't actually the main power. It's basically a big cutoff toggle that stops any power from flowing to the computer or the charger chips, thereby preventing it from gradually draining when not in use. The screen is glued into the front panel so that it doesn't fall out. The keys were a little bit tricky because there's nothing to really hold them in place until I put the front on, so I kinda had to do this upside down. And the whole metal front plate just gets secured by 6 M3 bolts. Pretty easy. With that done, let's test this thing out. The first thing you notice when you pick it up is how solid it feels. At its thickest, it's 36mm, or nearly 1.5 inches, and it weighs about a kilogram, or 2.2 pounds. Not exactly like holding a Game Boy, but not unmanageable. The screen on this device is extremely nice. It's really the perfect size, and it looks incredibly bright and sharp. And it is a touchscreen, but That's the one thing that's not currently working. There's nothing physically wrong with it, but for some reason it's not doing anything and it doesn't show up in Linux. But I decided that fixing this could wait, since it's not absolutely essential and I really wanted to wrap this project up. The keyboard is fine for what it is. The buttons are a little bit more clicky and have less travel than I would have liked, but there's nothing wrong with them. I can reach all the keys just fine, though to be fair, I do have fairly big hands. The layout is a little bit unconventional, standard QWERTY but in an ortho layout, which makes more sense if you think about it for thumb typing. This little top row has some keys that I couldn't fit into the main area, and these two buttons up here serve as left and right mouse clicks, although they can be remapped to whatever. And of course we also have the left and right trigger buttons on the underside of the case. As of right now, these are also just mapped to left and right click, although I'll probably be changing that soon. And then there's the scroll wheel. I love this thing. Such a fun and useful feature, and it looks really cool too, which never hurts. As for the joystick, it does the job. The biggest downside is that you essentially have to pick between speed and accuracy, but hey, you can always plug in a mouse to one of the USB ports. Speaking of which, you get 4. That's already better than a lot of modern laptops. At the top of the device in this indented area of the case is a full-size HDMI port. Great for when you want to use this thing at a desk with a bigger screen. And for that purpose, I 3D printed this dock, which makes the power plug accessible along with everything else. If you connect an external mouse and keyboard, you've got a nice little workstation ready to go. There's also this barrel jack. This was really just a carryover from my last design and shouldn't be used to power the device with the battery connected, but I left it accessible because it can still be used as a power output. Kind of a cool bonus feature. The battery system is actually the thing that I'm the most proud of on this project, even though it's the least flashy aspect to the casual observer. This was so much work, and having it pay off feels great. It's still not 100% accurate because there's a whole calibration regime you have to go through, and the software required has more of a learning wall than a learning curve. But I think I got it dialed in well enough for now. Under normal use, this little display shows the remaining capacity as reported by the fuel gauge chip. During charging though, it'll cycle through capacity, voltage, and input current. This is a full x86 desktop level system, so it can run any program that you'd be able to use on a regular computer. Performance-wise, it's very impressive for an SBC, although somewhat below that of a normal laptop. Linux helps with that since it eliminates a lot of the slop background processes that Windows gets bogged down by. It obviously doesn't have a discrete graphics card, so gaming is going to be limited to older titles or newer ones that have much simpler graphics. But this wasn't designed to compete with a Steam Deck or anything like that. This project was a huge amount of work and took way longer than expected, and don't even get me started on the cost. And even after all that, it's a little bit rough in some ways. I do have a long list of things that could be improved. That being said, I think it came out pretty good, but let me know what you think in the comments. Anyway, thanks for watching.